Okay, so today we'll start talking about the transversality theorems. So it's topic number 4. Okay, so we'll start with the definition of transversality. So let X and Y be manifolds, F a smooth function from X to Y, and W a submanifold of Y. We say that F is transverse to W at a point X in capital X if either X is not in the preimage of W, or if we have the transversality condition. So the derivative, if you push forward the tangent space of X and you sum with the tangent space of W, you get the whole tangent space of Y. And notice this is not a direct sum, so they could intersect. But we just want these two subspaces to generate together the whole tangent space of Y. Okay, so this is what it means for a function to be transverse to a manifold at X, and we say that F is transverse to W if F is transverse to W at X for every X in capital X. Okay, so that's what it means to be transverse. And a note is that on the introduction day, I talked about transversality a little bit, but I only talked about it in terms of submanifolds intersecting. And the note is that if you pick two submanifolds, X1 and X2, say submanifolds of Y, then they intersect transversely if and only if the inclusion of one into Y intersects, if the inclusion map intersects the other one transversely. Okay, so this is the iota, this is the inclusion map.
Professor.
Oi.
Então, meio que você pode definir transversalidade de mapas de um jeito mais geral do que...
Exatamente, essa é a ideia dessa definição. A gente está definindo a transversalidade de mapas.
Não, mas tipo, você pode definir a transversalidade entre dois mapas, em vez de um mapa e uma subvariedade.
Sim, mas é um pouquinho mais complicado, né? Porque, bom, na verdade, eu acho que você quer dizer que um mapa intersecta transversalmente a imagem do outro mapa.
Isso.
Então isso é um pouco mais... Sim, você pode falar isso, mas na verdade não é uma generalização.
Ah, tá.
É um caso particular, né?
É porque se você coloca entre dois mapas interceptando na imagem, a imagem do mapa não precisa ser necessariamente uma subvariedade. E aí o da subvariedade seria colocar a inclusão.
Ah, sim, sim. Não, tudo bem, é verdade. Você poderia falar isso. Mas...
Tem algum resultado sobre isso?
Tem. Eu não estou conseguindo me lembrar, mas eu acho que é um pouquinho mais complicado, porque você não vai conseguir os resultados de transversalidade, os resultados de genericidade. Porque se a imagem do mapa não for uma subvariedade, eu teria que pensar em alguns exemplos aqui, mas eu acho que a situação pode se complicar. Né? A gente falar em função transversal à subvariedade fica muito mais... A gente vai ter todos os teoremas bonitinhos que eu vou falar para vocês da aula de hoje. Basicamente, o teorema principal é que, dada uma subvariedade, você consegue perturbar a função para ela ficar transversa, mesmo se ela não for, inicialmente. A menos de uma perturbação, você consegue fazer a função ficar transversa à subvariedade. E no caso de uma variedade de duas funções, eu acho que você talvez precise perturbar as duas. Dado uma, porque se a imagem não for uma subvariedade, a situação, eu não sei se você consegue perturbar a primeira função para realmente ela ser transversa à imagem da segunda. Yeah, okay, that was a very good comment. So I think sometimes you can't talk about functions being transverse to each other, but yeah, it's definitely not as natural of a notion as the function being transverse to a submanifold. I'll think about it a little. I'll think about some examples maybe for next time. Okay. So let's talk about some examples of this definition already. So I actually think the most natural thing is for submanifolds to intersect transversely. And then we can talk about a function intersecting a submanifold transversely. Okay, so I guess the first example is we can just look at functions from R to R. And let's call F the graph of F. Which, by the way, is also what we call the zero jet of F. And it's kind of easy to see that the function, yeah, so what does it mean for this function, capital F, to intersect, say, I don't know, the x-axis transversely? So I have a function, I look at its graph, and I want it to intersect the x-axis transversely. In this case, it intersects transversely. But say in this case, it does not intersect transversely. So what you need to know, what basically you need to do is you need to just suppose that the function and derivative don't vanish at the same time. So there isn't a zero of order bigger than 1. So it's if and only if the preimage of the function of 0 does not intersect the preimage of the derivative. Okay. This is exactly the condition that you need for transversality. So if this is not obvious to you, I would say this you can do this as an exercise. But maybe for some of you, you don't need to write this down. But it's true. And notice that in this case here where you don't intersect, so this is not transverse. In this case here, it's not transverse, but you can perturb. If we perturb the function a little bit, then it becomes transverse. So you can perturb the function and get you can either get something like this, or you can get something like this. If you perturb the function slightly, then you're going to either have 2 zeros or no zeros. Okay? So a second example, which is kind of interesting, is now if I pick a function from R to R3, I'm just going to already pick the function like this. And say that this is a curve. So basically, you pick 2 curves. Okay? Here's a curve, and here, I don't know. Is another curve. how can these two intersect transversely? And this is a question that someone already asked. It's an example someone asked, I think, on the first class. So this can actually only happen if they don't intersect at all. The image of R, the image of F, does not intersect W. And it's because if they do intersect, then R has dimension 1, W has dimension 1, so the maximum dimension of the space that they can generate is 2. But we are in the space of dimension 3. Emphasize this is a curve in R3. Okay? So in general, I can state the proposition is the following. So let X and Y be manifolds, and F be a smooth function from X to Y, and W be a submanifold, such that the dimension of X is less than the codimension of W. The codimension just means the dimension of W minus the dimension. Sorry, the dimension of Y minus the dimension of W. Okay, so the condition is that the sum of the dimension of X and the dimension of W is less than the dimension of Y. Then F can only be transverse to W if the image of F does not intersect the image of W. Okay? Yeah, so like answering, I forget who asked the question at the beginning. You can talk about a function being transverse to another function, and a result like this would still hold. Yeah. And I think you could maybe actually phrase it in terms of the graph of one of the functions. I have to think about this, exactly what how to do it. But I actually think that two functions being transverse to each other is a particular case of this. And you have to just look at the graph of one of the functions. But anyway, I don't want to improvise right now. So I can prepare this and tell you about that next time. Okay, so what's the proof of this proposition? I already kind of said it in the example before, but let's write this down. So the proof is, so suppose that we have some element in X such that f of X belongs to W. So suppose the image of X intersects W, then the dimension of df x of tx plus the space that's generated by the push forward of the tangent space to X and the tangent space to W. This dimension is at most the sum of the dimension of X and the dimension of W. And we assume that this is strictly less than the dimension of Y, which is the dimension of the tangent space of Y to f of X. Okay, so F cannot be transverse to W at X. Let me put, I don't know how to write is not transverse because transverse already has a bar. So let me just write like this. Okay, so that's the proposition. And now we have the great theorem. So this is maybe the first theorem of today, and it's in a way just a reincarnation of the implicit function theorem, but I'm going to prove it because it's not so obvious. If you take the pre-image of a regular value that's a submanifold, that's pretty much a direct application of the implicit function theorem. But this is a little bit harder. So the theorem says that if you take two manifolds, and you take a submanifold such that F intersects W transversely, then the pre-image of W is a submanifold of X of codimension equal to the codimension of W. So that means, the dimension of this guy equals the dimension of X minus the dimension of Y minus the dimension of W. In particular, if the dimension of X is equal to the codimension of W, then the pre-image of W consists of isolated points. Okay, so actually thinking about it a little more, I think this theorem is the reason why we don't talk about transversality of functions that much. I mean, you can make the same definition, and this proposition still holds, but then sort of one of the main reasons you talk about things intersecting transversely is if you want to look at the intersection and say something meaningful. So that's one reason we don't talk about two functions intersecting transversely, because even if they did, using that definition, that wouldn't mean that they're that the pre-image of the image of one of them is a submanifold. Okay, like you can say, yeah, there is this generic condition of intersecting transversely, but if you don't assume the image of one of them is already a submanifold, then there's no reason to assume that to prove a theorem kind of like this. Okay. All right. Any questions about the statement of the theorem? No. Okay. So now we can prove. So you see that, maybe before the proof, remark if W is just a point in Y, then the function intersects W if and only if P is a regular value of F. And that's because the tangent space to a point is just a zero vector space. So the condition of intersecting a point transversely is that the derivative is surjective. So, that's because this intersects transversely if and only if dfx of txx is equal to t of p of y for every x in the preimage of the point. Okay, because the tangent space to a point is zero. And this theorem in this case really is a theorem I proved, I think, on the first class. Yeah, which is, or maybe the second class, which just follows directly from the implicit function theorem. Okay, and we're actually going to use this this theorem again. So we'll see that this is equivalent to this one, because that's the main thing that we need to prove this theorem. Okay, but we have to be a little bit smart about how to transform a submanifold into a point. Okay, so well, let's fix a point in the pre-image of y. Okay, so now for a point here, to not confuse you, let me call this point y, and let's leave p for a point in the domain. Let me just see if someone is trying to get in. No. Okay, so, and let me call, so I don't talk about dimension all the time, let's just fix n to be the dimension of x, n to be the dimension of y, and k to be the dimension of w. Okay, now, using, again, some version of the inverse function theorem, or, I guess this is called local, I don't know, the local form for immersions or something, just some version of the inverse function theorem, we can actually pick a chart. So we can be a chart around P, or around f of P, such that the intersection of the chart of the domain with W is just going to be the image of Rk times 0. Okay, so this is by one of these theorems that's equivalent to the inverse function theorem. So if you have a submanifold, then locally you can just assume that it's a neighborhood of a subspace of Rm. Okay. Does anybody have a question about this, or is this kind of obvious? I mean, this uses a heavy theorem, which is the inverse function theorem, but it's basically the same, or equivalent. Okay, so this is in any analysis book. Analysis on Rm. Okay, so we can assume that, and that's kind of what we need. And of course, we can always suppose that phi of f of p goes to 0, but this is actually 0. And now we can compose f with phi, and now we have a very canonical map. So now we can and we can write phi to be the composition of this. Well, this is also a phi. So for those of you who maybe don't know this, the usual phi in the Greek alphabet is this guy here on the left. But somehow some people, some of the Greeks also liked, there was a second way of writing a letter. So it's kind of like writing A like this and writing A like this. There's just two ways of writing the same letter. But in math, we kind of differentiate them often. So I'm using this phi as kind of a, something related to this other phi, and I'm going to call them both phi. But it's just what happens when I project to Rn minus k. So when I project to the orthogonal complement of this guy. So P is a map that goes from Rm to Rm minus k. So this is the orthogonal complement. I mean, you can think of this as just being Rm quotiented by Rk times 0. Okay, so phi is now a map from U to Rm minus k. And phi in the pre-image of 0 is just U intersection W. So basically, I I created a map whose pre-image of 0 is just W itself. I mean, in this open set. Okay, and it's also pretty clear that this phi is a submersion. That's because the projection is a submersion. I mean, the projection is a surjective map, and phi is an embedding. Okay, because it's a chart, so it's a diffeomorphism onto its image. That's because derivative of this at some point, y is just pi composed with d phi at y. Okay. And this guy is a bijection, and this guy is a surjection. Okay. So now, the idea is that I want to compose f with this phi here. And then I'll actually get a map. Then I'll be able to replace w with a point. And then I'll be able to use the implicit function theorem. So the claim is that f is transverse to w at p if and only if if and only if 0 is a regular value of phi composed f. Or actually, no, I think to be more precise, it's not exactly it. I would have to do it for every pre-image. So if and only if phi composed with f is transverse to 0 at p. That's the statement that's actually true. Okay, so this is what I was saying. You replace the condition of being transverse to some submanifold to the condition of just being transverse to a point. But then if you change the function a little bit, you compose it with some submersion. Okay? And if this is actually true, then we're done. Because if the claim is true, then we are done. And that's because, well, in this neighborhood, W is just given by the pre-image of 0. So we know that if this condition on the right is satisfied, so if phi composed with f is transverse to 0, then the pre-image of 0 by this guy is a manifold. But this is just the pre-image of the pre-image of 0. And this guy here is just a W, but in this neighborhood. So then this would be a manifold, and the dimension is equal to the dimension of the target space of this function. Sorry, the codimension is the dimension of the target space. So the codimension the dimension of codimension equal to the codimension of the point. So the codimension will be equal to m minus k. This is the dimension of this is the domain, the target of this map. So this map, the target of this map is this Rm minus k. Okay, I mean and then we do this locally, and because being a manifold is a local concept, then we're done. Okay, so we need to prove this claim. Is this clear, or does anybody have a question about this thought process?
Can you repeat, please? Why?
Yeah.
if the claim is true, it's over?
Yeah. So if the claim is true, so what we're trying to prove is that the preimage of W is a manifold, and we're going to prove that locally. So near each point on the preimage of W, then we have locally a manifold. Okay. So the claim is we only need to do it locally. So what we did is like near P, we found this function here. I mean, we found this phi, and we claim that this condition holds if and only if we can compose F with some submersion such that this is transverse to 0 at P. And that's true for every point locally. Okay, actually, yeah. So if this claim is true for every point in the preimage of W, then you can actually do this locally. There's a step here that I didn't write down, but you have to do it locally for a chart around P that is sent to U. Okay, so this is the step I'm kind of skipping, but this is kind of standard. But I guess the main equality to keep in mind is this one. So if you take what's the preimage of 0 of this composition of F with the submersion? Well, this is just the preimage of phi inverse of 0. And phi inverse of 0 is W in this neighborhood. Okay, and then the implicit function theorem will tell you, or this manifold's version of the implicit function theorem will tell you that this, the preimage of a regular value is a manifold. And the dimension of the codimension of this manifold is the same as the codimension of the point. So it's the dimension of the total space. Okay, so this is saying that locally, is it clear? Or
yes.
Okay.
Like you locally write it as the preimage of a regular value, and doing that for every point.
Yeah.
Okay, I got it. Thank you.
So you replace the preimage of a submanifold by the preimage of a regular value of another function. Okay, that's the key idea of the proof, and you just have to find what this function is, and you can't define a function globally in general. You have to do it locally, but that's okay. You can do it locally. Okay, so now we have to prove the claim, and I mean the claim is just some basic linear algebra or differential analysis on our end, but I think we should write it down. So yeah, so from the condition of being transverse, this is equivalent to writing that, I mean, you have to consider, well, we already are assuming that P is in the preimage. So if P is not in the preimage, then it's going to be transverse. So if it's transverse at P and is in the preimage, then we can write it, we can write the equality of the linear algebra. So we have this condition. These two subspaces generate the space of Y, which, I mean, the tangent space to Y is the same as the tangent space to U, because U is an open set. Okay. And now we precompose with d phi at f of b. Okay, so when we precompose with d phi, we get that d of phi composed with f, well, at p of tp x is equal, well, the second part here is projected to 0. Like by phi, phi projects w to 0, so this part here dies. And then we get d phi at f of p of TFB of U, and that's just the tangent space to R m minus k at 0. So this, in this condition here, is what it means. This is an if and only if this is the condition of being transverse to 0 at P. Okay. So if you want to be, even more precise, you could maybe do this. You can find a phi that works in a local neighborhood of P. And then you can do this kind of locally around P. But this is the condition that you need. Okay? And I mean, it's obvious that you can precompose with d phi, but because phi is a submersion, this guy is a surjection. This derivative is a surjection, so we can also go back. So this is actually equivalent to this condition here. Okay. So that's the proof of the claim, and that's the end of the proof of the proposition. So again, let me say one more time. The proposition says that if you have a function that's a smooth function that's transverse to a submanifold of the target, then the preimage of the submanifold is still a submanifold with the same codimension. And the proof is just finding a submersion such that when you precompose the function by the submersion, with the submersion, you actually get that the transversality condition is equivalent to it being a local submersion at near a point. Okay. Which is the same as intersecting 0 transversely. Okay, so now let's, so far this is still not too, doesn't use very heavy theory, it doesn't use jets yet. So now let's get a little bit, let's move on to something a little more abstract, which is the following, which is a proposition which will be useful in the big theorem of today. So let X and Y be manifolds. And let's pick a submanifold of the target, which is also a closed space, which is a closed subspace. So when I say closed subspace, I mean a closed, as a subset of Y, it's a closed subspace. And I'm emphasizing that because a closed manifold is usually meant to be compact as well. And this is just a slightly confusing notation, but usually in geometry, people talk about a closed manifold or a closed submanifold as a manifold or submanifold that's also compact. And that's not required for this proposition. It just means to be closed as a subspace. Then we can look at the set of functions which are transverse to W, and this set is open in C infinity. So the set of functions which are transverse to a given subspace is an open set in the C infinity topology. So let me write in the C infinity topology, but I'm going to stop writing this. Like when I say it's open in this set, the topology is assumed. Okay. So the proposition is even stronger, and we're going to prove that it's open in the C1 topology. This, as you see, this is going to be a corollary of a much heavier theorem, transversality theorem, but we need this little fact to prove the big transversality theorem, which we actually are not going to do today. But so we're gonna kind of this proposition is to warm up, and it'll be necessary. Okay, so let's understand it well. So what I'm saying is, if you fix a submanifold and you look at the set of functions which are transverse to the submanifold, that's an open set in this infinity topology. Okay, so we actually will prove that the set is open in the C1 topology. So since the C1 topology is contained in the C infinity topology, then it's going to be open in the C infinity topology. So how do we do that? Well, we're going to let U be an open set in the jet space, in the one jet space, and it will show that this TW is basically the set generated by this U. So let U be the set of jets. So the set of one jets. Every one jet can be written as the one jet of a function at a point x. Remember, this is the same as the equivalence class of f at the point x, such that basically the transversality condition holds. df x of tx yeah, I'm gonna spell it out. Is equal to t of f of x, y, or f of x does not belong to W. Okay, I want to write it down instead of just saying f is transverse to y to W, because we have to really see that these conditions will give us an open subset. So this is a subset of J1 of xy, and it's pretty clear that TW is just this M of U. Remember what M is. This is just the set of functions such that the one jet of F has image contained in U. Okay, this is just basically the definition of transversality. Okay, so what do we need to prove? We need to show that U is open. Because remember that the C1 topology, or the CK topology, is generated by these sets, M of U, where U is an open set of the jet space. So if we prove that the set that we define here is open, then we're done. Then this guy will be an element of the base of the C1 topology, and therefore it will be an open set. Okay, so we need to show U is open. And instead of showing that U is open, we're going to show its complement is closed, because it's easier. So we claim that V, which is the complement of U, is closed. Okay, so now let's prove the claim. And that's the end of the proposition. It'll take a little time, but so let sigma n be a sequence of jets contained in V. Sequence such that sigma n converges to sigma in the C1 topology. Sorry, not in C1 topology, in the jet space, so in V1. Okay, so we need to show that sigma is also in V. But the limit of the sequence is in V. Okay, so let's write the following. So first of all, since B is continuous, B of sigma n, beta of sigma n converges to beta of sigma. Remember what beta is. Beta is just the target. So if you write, if sigma n is the jet one, the one jet of a function, beta of sigma n is just the image of the function. So since beta is continuous, beta of sigma n is beta of sigma. So sigma n is the one jet of a function fn at the point xn. Then O alpha is also continuous, so xn converges to x, and sort of fn of xn converges to beta of sigma. Okay, so if you can write sigma as the one jet of f of x. Sorry, I think this is what I really mean. So if I write sigma as the one jet of f of x, then xn converges to x, and fn of xn converges to f of x. And this is because of that. So sorry, let me write this again. Since alpha and beta are continuous. Yeah. So since the source and the target are continuous, when you write down your when you write down the jets, the one jets like this as one jet of a function at a point, then we have that the point converges and the value of the function also converges. Okay. So now we can pick a chart. Now let u, phi, and we're going to pick charts around x and f of x. So let phi and c, well, should use another u. So u tilde mc that goes from v tilde to our m be charts around x and f of x. We can assume, as we did before, as we did in the previous proposition, that psi of v tilde intersection with w is just rk times 0. And we also assume, for simplicity, that phi of x is 0 and psi of f of x is 0. Okay? So now the condition, so basically now we can look at everything locally, because so the xn is convergent to x, so eventually the xn will be in u tilde, and the fn of xn will eventually be in v tilde. So that means that we can translate the problem to a problem just in Euclidean spaces. So so we can assume that x is Rn, y is Rm, and we can assume that w is Rk times 0. And we can assume, x is 0 and f of x is 0. Okay? So, so now the condition of being transverse at x is equivalent, is basically the same as being transverse to Rk times 0 at 0. Okay, so now let's look at what V is. So V is the complement of U, and U is the set of jets here, such that either this condition of transversality is true, or f of x does not belong to W. Okay? So V is going to be the set of jets such that this condition of transversality is not true, and f of x is in W. So to show that V is closed, we need to show, well, first of all, that f of x is in W, and that this condition does not hold. So we need to show that f of x is in W, and the condition of transversality plus t of f of x W is a subset, but it's not equal to the whole thing. Okay, so first of all, I guess I could have said this before choosing charts, but the first condition is going to hold. So this condition holds because W is closed. And so we know that Fn of xn belongs to W. So we have a sequence, and xn is continuous, and Fn converges to F. So it converges and Fn of xn by assumption converges to f of x. So since these guys all belong to W, then f of x also belongs to W. Okay, so the first condition is easy. So what we need to show now is that the second condition also holds. So that means that f is not transverse to W. So the claim is if we take a sequence of functions and sequence of points where the functions are not transverse to W, but both the points converge and the functions at the point converge, then this transversality condition does not hold. Okay, so now we have this chart. We chose charts in the domain and in the target, and the point is that f is transverse to Rk times 0 at 0 if and only if zero. Now we do something similar to that other thing. If and only if yes. 0 is a regular point of pi composed with f, where pi is the projection that grows from Rm to Rm minus k. Okay. This is the same argument that we did before. So, but now we're already in the Euclidean space. But we could have just kept it in charts as before. But you see why I'm already kind of doing everything in charts in Rm to simplify my life, is because I want another equivalence here. So this is equivalent to saying that the derivative of this map, so pi composed with df at 0, has rank m minus k, has maximum rank m minus k. We're supposing, remember, that n is greater than or equal to m minus k. Yeah, so this is less than or equal to n. otherwise the claim is simple. Yeah. Otherwise, this V is empty because U is everything. No, sorry. Otherwise the result follows from by Start's theorem. I'll say this in a little bit. But anyway, we want this to have maximum rank, which is m minus k. So we can actually look at the set of matrices, the linear maps from Rn to Rm minus k, such that the rank of A is less than m minus k. And we can actually, when you look at the jet space from Rn to Rm, we can just project it to the set of homomorphisms, which is by just, when you look at the one jet of a function, you just take the derivative of the function at the point x. And that's a homomorphism. Okay. And this function eta is continuous. And moreover, the inverse of V, no, the inverse of F is precisely V. Or, V looked in coordinates. So if you want, yeah, we have to be completely careful. We have to look at, you have to use the charts. So phi, inverse, star, and then psi, go back of V. But anyway, these guys are diffeomorphisms. So what we remain to do is to show that this F here is closed. But that's linear algebra. Closed by linear algebra. So how do we show the set is closed? If you fix a rank, then the set is closed. And this is the finite union of matrices of rank 0, 1, 2, 3, up to m minus k plus 1. So this set will be closed. Therefore, basically, therefore, V is closed. Or, to be completely honest, you really have to. You can only do this locally. So, yeah. So to be completely honest, you have to intersect with U tilde, and therefore the conclusion is that sigma is in V, and hence V is closed. And that's the end. Sorry, this was a little back and forth, but I guess the main point of the proof, well, there are two things you have to prove, which is that the limit still has the property that f of x belongs to, is always in W, and that comes from the closeness of W. And then the second condition is just this follows from the linear algebra fact that the matrices with rank less than m minus k, this forms a closed set. Okay. And the remark is that this proposition does not hold if W is not closed. So in general, if W is not closed, we can find examples where the proposition doesn't hold. So for example, I mean, I think it's pretty easy to find an example, but let's just think about the easiest one I can think of. Is take the circle, for example, and consider, think of this as just the image of a curve. So this is basically an embedded curve. So it's a map from the circle to R3. And this is the image of the map. Okay, so this picture is terrible. Think about the circle S1 in here, and this is in R3. Now the picture is better. And then let me consider the submanifold, which is, I don't know, some curve, some open curve that wants to touch the circle but doesn't touch it. So this is my submanifold W. And notice that this curve, F, intersects gamma transversely because they don't intersect. But you can perturb your curve so that it does intersect. So we can find, for example, a sequence of Fn's converging to F in the C1 topology, such that Fn of S1 intersects W. So that means they cannot be transverse because there's two curves in R3. Okay, so, and that's because W is not closed. Because W is not closed, this does not contradict the theorem. Okay? I mean, I think you can think about more interesting examples, but this is just the simplest thing I could think of. And I said that I was going to say something about the case when the codimension is so in the case when the codimension of W is bigger than the dimension of X, what happens is this first condition is never satisfied. So U is just a set of points where f of x, whose is a set of one jets whose image is not contained in W. And this set is clearly open. Okay, it's clearly open by this this reason here. Okay, sorry, I didn't write this down because this was the easy case, but I think I should have said that. Okay. Although, yeah, if you replace m minus k by maximum rank, no, I think it's I should have still said that. Okay. Any questions about this?
Você pode repetir esse último exemplo? Eu não entendi direito.
Esse exemplo daqui?
Isso.
Yes, I can repeat it. So what I'm saying is that if you don't assume that W is closed, then it's not true in general that the space of functions that's transverse to W is open. So I'm giving an example of one function that does not have a neighborhood that contain, one so I'm giving you an example of a function in a subspace such that f is transverse to W, but I can find a sequence that converges to f in C infinity such that Fn is not transverse to W. Okay, so this proves that this set of functions which are transverse to W is not an open set. But if I do the example where x is R or S1, for example, and y is our 3, and w is a curve, a one-dimensional thing, then being transverse is the same as not intersecting. So f is transverse to w if and only if the image of f does not intersect. Okay, so now if I pick, for example, I can pick an embedded curve like this, any circle, and if I pick a curve that's an open curve, so something like this, I don't know, it could be, anything, but some curve that's open, but that doesn't actually touch here. So, my W here says the image of some open interval. Okay, but and G, if you, I don't know, I can write this down, but I think you know what I mean, right? I mean, you can think of G as being a closed curve such that G of A belongs to f of S1. Okay, but then if you look at just the image of the open interval, and G of AB does not intersect f of S1. Okay, so what I'm saying is, in this case, I can actually perturb I can find a function Fn such that they go like this. So you see that I'm going to have a sequence, they're always going to intersect except for f. So I'm saying that Fn of S1 will intersect W for every n. And Fn converges to f in the C-infinity topology. I mean, if you want, you can write this very explicitly, like, since we're doing this, let me write it. So f of t is equal to cosine t, sine t, and 0. And W is the image G of 0, 1, where G of t is, I don't know, t 0, 0. Okay, there we go. Okay, so we are in this plane. We have this circle, and then we have this curve. And the point is, you can write Fn of t to be cosine of t minus 1 over n sine t 0. And now you can see what I was saying. This example that I wrote explicitly satisfies this hypothesis, which is that f of S1 does not intersect W, but Fn of S1 intersects W for every n. Okay, is that clear now?
Sim, sim, sim. Obrigado.
Que bom. De nada. Okay, so now I need to prove a lemma that's a little bit... Now we're getting slightly more technical until we get to the big theorem, which I think at this point we'll prove next time.
Can I ask one more question?
Yes.
Maybe you said it before, but I didn't get it. But
yeah.
Why being open in the C1 topology implies being open in the C-infinite topology?
Because the C1 topology is contained in the C-infinity topology. Remember what the base is. What's the base for the C-infinity topology is the union of all the bases of all the CK topologies.
Okay.
Yeah. So yeah.
Thank you.
And if you think about closed sets, it's the opposite. So if you want a convergent sequence, it has to converge for all the CK topologies.
Okay.
Yeah, which is what you think. All the derivatives have to converge.
Okay.
Yeah.
Thank you.
You're welcome. So here's the lemma. The lemma is going to start to really smell like the genericity condition that we want. So let x, b, and y B manifolds. And let's pick a submanifold of, as usual, now we have an extra B, which is going to be the parameter of functions that we want. And let J be a map. So basically, we're choosing functions parametrized by some parameter that lives in another manifold. This is a map. And surprisingly, you don't actually need this map, any condition on the map. So this is not necessarily continuous. Although I think in practice it often is. But I think for the proof I think we need to consider one case where it's not continuous, which is why it's in a lemma. But now we can think of this function. Yeah, because being continuous would mean that it's continuous in the infinity topology, and it's kind of a strong condition. It's yeah, because here the topology is the infinity topology. So let this map given by this is just the image of JB of X. So it's just kind of a different way of thinking about the family of maps. And now we suppose that this map phi is smooth. And that this map phi is transverse to W. Okay. So before I say what the conclusion is, let me just say this one more time. So we have a family of maps, and there are two ways to think about a family of maps. One is you can think about a map like this on the product, or you can think about a function that goes from the parameter space to C-infinity functions. Okay. And this condition of being smooth is different from J being continuous. So maybe an exercise here is to find, maybe it's slightly tricky, but maybe like it's kind of a functional analysis exercise, but to find a family of functions like this, which is smooth in this sense, that phi is smooth, but that J like this, little j is not continuous. This is maybe a good exercise for between now and Thursday. The conclusion is then the set of points B such that J of B is transverse to W. This is the same as phi of dot B. Is dense in B. So in other words, this is maybe like the first well-known transversality result. It says that if you have a family of functions, and the family of functions as a family is transverse to a submanifold, then for a dense subset of parameters, the function from X is also transverse. Okay, so this is very often used for homotopy. So like if B is an interval, so let's say if you have a homotopy of functions parameterized in an interval, and the homotopy is transverse to a submanifold, then each function, or there's dense subset of parameters such that the function at this parameter is transverse to the submanifold. Okay. So that's the lemma. Okay, so let's prove this. So first of all, so we're assuming that this homotopy, or this family, is transverse to W. So the first thing we can do is we can take the pre-image of W by this phi. So we let W phi be the pre-image of W. So this is something in X times B. Are there any questions so far before I go on with the proof?
phi has to be smooth.
Yes.
Okay. Ah, okay.
Yeah, I mean, I think we might not need it to be C infinity. We could maybe have it to be just C1. But I don't want to get into that. As I said at the beginning of the course, I'm not going to worry about differentiability questions, C1, C2, C3. But yeah, I'm just assuming everything is C infinity. Yeah, otherwise, you can't even talk, if it's not differentiable, you can't even talk about transversality. Yeah. And I said the exercise is to think about how this condition of phi being smooth is related to this J being continuous. So I don't want to get into that now. It's a little technical. But you can think about that. Okay, so first step is, kind of obvious. We have some transverse intersection, and we just pick the pre-image. And now, I'm going to call PR the projection onto B of X times B. And by P, I'm going to denote PR restricted to this submanifold W phi. Okay, and we claim, or let me just write claim, is that if B is a regular value of pi, then J of B intersects W transversely. Okay? And this claim, now by Sard's theorem, this claim implies a theorem. And also, by Sard's theorem and the fact that C infinity is a Baire subspace, is a Baire space, I should say that. By Sard's theorem, since C infinity of xy no, sorry, I don't need that. Because B is a manifold, so B is a Baire space, just because it's a manifold. Oops, I think I can't go back now. I have to write it again. Yeah, so by Sard's theorem, this set of B's satisfying this condition here contains the set of B's which are regular values of pi. So by Sard's theorem, this set is dense, therefore this set is going to be dense. Okay? By Sard's theorem, and because B is a manifold, so a manifold is a Baire space. So by Sard's theorem, the lemma holds. Okay, so we just need to show the claim. Okay. The proof. So first of all, let's suppose that B is not in the image of pi. So everything that's not in the image is a regular value by definition. So if B is not in the image of pi, then that means that there doesn't exist some x in x such that xb belongs to W P. Okay, so that means that's the same as saying that phi of xb belongs to w, which is the same as saying that j of xb belongs to w. So this is pretty, it's kind of a tautology almost. So that means that j of x, little x, sorry, I did it the other way around. J of b is a function, and then you apply that to x. So that means that j of b, the image of j of b, does not intersect w. Is equal to the empty set. So, you know, that's a way of being transverse. So j of b is transverse to w. Okay. So this is in general for a point that's not in the image. And then now I'm going to write it maybe a little better than last time, than the last proof. I'm going to write explicitly what happens in the when the dimensions don't satisfy a good condition for transversality, or you know, for the transversality equation to make sense. So so suppose the dimension of w phi is less than the dimension of b. So if that's the case, then if b is a regular value of pi, then this, you know, implies that b cannot be in the image pi, and then by 1, j of b is transverse to w. Okay, so basically what's left to show, and that's kind of the main part, is what happens if the dimension of w phi is bigger than or equal to the dimension of b. Okay. So now let's do that, and let's fix let b be a regular value of pi. Okay, we need to show that j of b is transverse to w. Okay, so let x be a point in x. We need to show that j of b, we need to show that j of b is transverse to w at x. So if, well, I guess, you know, we have to show this for every x. So if the xb is not in w phi, then that means that phi of xb is not in w. So this is the same as j of b applied to x. So that means that x is not in the preimage of w. So that means that j of b intersects w transversely because it's a vacuous condition. Okay, so basically I'm kind of dusting off all of the little trivial things that we need to dust off before showing kind of the inequality, which is when things do intersect. Okay, now suppose that xb is in w phi. So that means that phi of xb is in w. Okay, so first of all, because pi is a surjective map, we can split the tangent space like this. So the tangent space of x times b is equal to the tangent space of wb plus the tangent space x times b. Okay, and that's because b is a regular value of pi. Okay, so because b is a regular value of pi, when you project by pi, this first term goes to 0 because you're projecting onto b, and then this guy is the tangent space to b, and then this is the image of pi, of d pi, which is the same yeah, which is the same as pi, because pi is a projection. So because b is a regular value, we have to have this equality here. And because pi, yeah, pi is surjective. Okay? That's because, you know, the surjective map satisfies pi inverse composed with pi as the identity. Okay. This is just the linear algebra detail. So we have this. So now we can apply d phi and xb. So when applying d phi, we obtain, well, here we get d phi xb of t xb of x times b. And then here, when you apply d phi, you just get the tangent space of w, because that's how w, you know, by definition, phi inverse of w is w phi. So here we get the tangent space of w at the point phi of xb. And then here we just get the j of b. And when you apply phi, you just get the push forward of tx of x. So you're differentiating just on the x part. Okay. And then this first term here, now since phi is transverse to w, now you can write this guy here. We have that d phi of xb of txb, the total space, you can write it as this, oops. No, sorry. The derivative of this guy plus this guy is equal to the total space. Okay. But you see that with the assumption that we have, so which is that b is a regular value, this subspace is already contained here. So we don't even need this part here to generate the whole tangent space of y. This implies that this tangent space, this derivative here, is already the tangent space of y. So therefore, the tangent space to y at the point, I mean, now we can write j of b at x is equal to this guy here, which is the tangent space at g of b at x, plus now the derivative of the differential of g of b at x. Oops, I forgot to write w at tx of x. Okay, so j of b is transverse to w at x. That's the last thing. And that's the end. Any questions?
Você poderia repetir essa última parte? Você aplicou, define os dois lados, né? E aí como é que chegou nesse último resultado?
Talvez o único que seja não completamente óbvio, né? Talvez seja o último termo. Então vou colocar isso aqui como exercício. Mas, assim, é um exercício de definição, mas não deixa de ser, não é uma coisa talvez inteiramente óbvia. O exercício é que dφ de xb aplicado ao espaço tangente de x vezes uma fibra xb, isso aqui é igual a djb de x de tx de x. Onde j J de B exatamente φ de ponto B. Okay, I think, you know, to get this, you just have to look at this equality and look at the inclusion of x in x times b. Okay, so if this is a little tricky, if this example is a little, sorry, if this implication is not obvious, maybe you should do this exercise. Okay. And then this one is just because this is the pre-image of this. So when you push forward the tangent space, it's equal to this tangent space. This is maybe a consequence. Maybe I should have said this when I proved the proposition. This is another part, is that the tangent space of the pre-image is taken to the tangent space of the submanifold. Yeah, so I guess maybe the first one is obvious. This one is obvious. This one is maybe not completely obvious, but this implication here is because when you take when F is transverse to W, then the tangent space, when you look at the tangent space of the pre-image and you push it forward by dF, this is the tangent space at F of X of W. This is part of the implicit function theorem argument, but I think I forgot to mention it. And then the third step is this here, which I think you might be able to just rewrite it like this. But yeah, it's some exercise of notation, but I think it can be kind of confusing if you haven't thought about these things very much. Anyway, then the second part is, because we're assuming that the big map phi is transverse to W, then we have this inequality here. That this push forward of this tangent space and the tangent space of W together generate Y. But in the particular case that we have, which is when B is a regular value of pi, this actually implies that this tangent space here is already contained in this one on the left. So, you know, basically we can get rid of it. And then we have that this is equal to the total tangent space of Y. Okay, so we can replace this on the left by the total tangent space of Y, and then we get the transversality condition for J of B. Okay, so if you think about examples, maybe this this lemma is not so, this condition is not so bad, and you really see that the lemma just follows from Sard's theorem. Okay, so a corollary is that we can do something like this for higher jets. So a corollary is that, say you have a family, a smooth family of maps, and say you have I mean, this corollary is just something that's going to be used in the proof of the main theorem. And let me write it down. So let phi, I actually want phi to be the kth jet of F of JB, of J dot B. So if we assume that phi is transverse, and we pick a W, we let W be a submanifold of the space of jets. And now we assume that phi is transverse to W. then the set of B's such that the kth jet of this, well, sorry, I think the way I'm writing the corollary is completely obvious. So let me write something a little bit. Yeah. Okay, let's do it like this. Okay. So it's a little, even though I'm doing it live, it's still a little bit different from a Blackboard. So choose a family of functions, pick a subspace, a submanifold of the space of jets, and let GB be the function G of dot B for B and B. So JB is a smooth function from X to Y. Then the set of B's in B such that the kth jet of GB is transverse to W. Now suppose now I think I still have to suppose that the kth jet of G, well, sorry, I was trying to simplify it, but I'm messing it up. I think I still have to write this for you, but I think I'm just following the book, but I think it's kind of an obvious corollary. But anyway, let me write it down. It's more like summing up an idea. So anyway, we define this phi, which is the kth jet of JB at the point X. So, and we have to suppose that phi intersects W transversely. Then the set of points B and B such that the kth jet of JB is transverse to W is dense. Okay, maybe it's not completely trivial, but the proof, it's kind of straightforward. But I guess the point is the idea that if you have a family of maps, you can also look at another family, which is the family of the kth jets of these maps. And then if you suppose that this family is transverse to W, then the set of points where the jets are supposed to are transverse to W is dense. Okay. So anyway, I'm just writing this, but I think I don't have time to prove the theorem. But let me state the theorem, and then we'll prove it next time. The theorem, which is Thom transversality. And this is kind of a big bomb, and mostly we will use the theorem in special cases. So, but we're just going to prove the big bomb. So let X and Y be manifolds, and let W be a submanifold of this jet space. Now let TW be the space of functions such that the kth jet of F is transverse to W. Then TW is a residual space, a residual subset of C infinity. Residual subset means that it's a countable intersection of open and dense sets, which implies that they are dense by the theorem from last time. Dense because C infinity is bare. Moreover, if W is closed, then TW is an open subset. Okay, so this is a heavy theorem because it's a theorem about jets. Because it's heavy, the proof is kind of intricate. But I just want to mention a corollary, which is maybe the traditional transversality corollary, which is the traditional transversality theorem. Which will be useful. Maybe the most useful for us will be the corollary, but sometimes we might want to use the full Thom transversality theorem for higher derivatives. But the corollary is, if we just have the situation we typically have, which is two manifolds and a submanifold of Y, then the set of functions which are transverse to W is dense. And if W is closed, this set is open. Okay. We already proved the second part. The proposition that we proved a little while ago was that this set was open when W is closed. Okay. Well, let me just leave it like this, and then the other part of corollary I'll talk about next time. Okay. So anyway, let's stop here.